Okay, we're going to talk some more about the normal distribution in this video. So, in any distribution, the tails are the more unlikely things, and that's what we're going to be really focusing on a lot, is the less likely things, not the people in the middle, the people who are either way above average or way below average. And so I want more accurate z values for certain parts of the tail. Okay, and here are the most commonly used areas and their z values that we're going to use. So if you want a tail area of 0.1 or 10%, the z number is 1.282. If you want 5% area in the tail, it's 1.645. 2.5% is 1.960. 1% area is 2.326. And if you want 0.5% area, it's 2.576. These are really important numbers. You're just going to have to either commit them to memory or for sure put them on your sheet of formulas. So these are correct to 3 decimal places. The z table only goes to 2, so it's not quite accurate enough as these numbers here. When you're doing problems and I ask for these various areas, if it comes up, use these numbers. Okay, so let's see how we use it. Back to SAT, which is normal with a mean of 500 and an SD of 90. 95% are between what two numbers? And of course, I'm referring to the middle 95%. That means that 2.5% is in the left and 2.5% is in the right. Well, 2.5%, as you just learned, is 1.96 in the z table. So it's between negative 1.96 and positive 1.96. That's the middle 95% of area. And this is actually, you may have heard me refer to the plus or minus 2 SDs as being very likely. Well, this is almost 2 SDs. 2 SDs would be 2.0 exactly. 1.96 is almost 2 SDs, but that you get the idea. It's essentially plus or minus 2 SDs, almost. Okay, so since z is either negative 1.96 or positive 1.96, I take these two numbers and I convert them back into x. So this is the formula for z. It's x minus the mean divided by the SD. And I'm going to solve each one for x. So the lower x is 323.6. The larger x above average is 676.4. And that's the lower and upper bounds of that area of 95%. Okay, let's go back to heights, which are normal with a mean. Oh, an unknown mean this time, and unknown SD. So let's see how this works. So you're given the information that the 10th percentile is 146.5 and the 95th percentile is 182.3. So based on that information, we should be able to figure out the mean in the SD. If you're paying attention, you might notice that I gave you 2 percentiles. This is going to, and we have 2 unknowns. We're going to have 2 equations and 2 variables. But here's the picture. The 10th percentile is well below average, and it's given to you as 146.5. The 95th percentile is way above average. Only 5% of people are above it. And from before, we know what these z values are. The lower one is negative 1.282. And the upper one is 1.645. Those are the z's with those particular areas. So my 2 equations and 2 unknowns. Well, there's the lower one, and there's the upper one. So, simplifying a little bit, I have these two equations, and this is perfect for elimination. I'm going to subtract and eliminate the mean. And I can solve directly for the standard deviation. And once I have that, I can plug it back in and find the mean. And so I found my two unknowns here. But it's a matter of solving two equations with two variables. Okay. There are ties between the normal distribution and two distributions that we learned in the past. So the binomial distribution, if n is large, can be very accurately approximated by a normal distribution with the mean and variance as given by the binomial distribution formulas. So you might be asking yourself, what is large? I mean, it says if n is large. What is large? Well, there's a rule of thumb that n should be big enough that n times p and n times q should both be at least 5. If you don't have this, then n is definitely too small. But of course, there's one more thing to mention, though, and it's that the binomial distribution is discrete. It can only be a whole number, but the normal distribution is continuous. So we have to apply something called the continuity correction. So when you're thinking about whole numbers, every whole number takes up some space to the left and right, specifically 0.5 to the left and 0.5 to the right on the continuous number line. So if I want the probability of 25 exactly, I'm going to go between 24.5 and 25.5. That whole range corresponds to 25. And if I want 1, 2, or 3, I'm going to start 0.5 below 1 and go all the way up to 0.5 above 3. So from 0.5 to 3.5 on the continuous scales. That's the continuity correction. When you go from the whole numbers in the discrete distribution to the continuous distribution, you have to think about going 0.5 to the left and 0.5 to the right. Okay, so let's go back to Shaq. And remember, Shaq, he makes 60% of his shots, so that's binomial. And he's going to make 800. That's definitely large enough. So 800 times 0.6 is 480. 800 times 0.6 times 0.4 is 192. That's the variance. Remember, that's the variance, not the SD. The square root of that is the SD. Okay, so I want to find the probability that he makes at least 475. So that's x greater than or equal to 475. Remember, since this is only whole numbers, or equal to matters here. So when I switch to continuous, it's going to be everything greater than 474.5. That's what I'm going to plug into my normal distribution. Okay, so to go to normal, I'm going to subtract the mean from both sides and divide by the square root of 192, the SD. And that creates z, and it's the area greater than negative 0.4. So go to the z table. And don't forget the trick that the area greater than negative 0.4 is the area less than positive 0.4. So looking up 0.40, I get my area of 0.6554. Okay, and there's also a normal approximation for the Poisson. And it also depends on the expected value being large. So the expected value should be, as a rule of thumb, it should be at least 30 to be safe. But the larger it is, the better the approximation is. And remember, at the Poisson distribution, the mean and variance are both the same. They're both the expected value. and that's going to be the mean and variance of the normal distribution. So we have cars going through an intersection at a rate of 500 per hour. I want the probability that between 1,944 and 1,977 inclusive, so that means or equal to, cars go through the intersection in 4 hours. Okay, so first of all, thinking about the 4 hours, at the rate given in 4 hours, we'd expect 2,000 cars. So that's the mean and the variance of the normal distribution. Okay, so it's the highlighted area there. They're both below average. Anyways, it's those numbers inclusive, so it's less than or equal to and less than or equal to. So that means when I switch to continuous, I have to go 0.5 below and 0.5 above. Okay, now to create z, you subtract the mean and divide by the SD. Remember, the SD is the square root of 2,000. And so z is between negative 1.26 and negative 0.5. All right, so going to the z table. So the area to the left of negative 0.5, let's look up 0.50. Well, the area to the left of negative 0.5 is the same as the area to the right of positive 0.5. Hence, I subtract from 1. And the same trick with negative 1.26. 1.26 has an area of 0.8962. Subtract that from 1. And we get an overall answer of 0.2047. Okay, so these are more tricks about the normal distribution that are very helpful. And those tail areas that I mentioned in the first couple of minutes are very important. We're going to use them extensively in the rest of the term. So make sure you definitely have those written down somewhere safe. All right, and I'll see you in the next video.